This is Dr. Carroll, and this is another video about greedy algorithms, specifically about Huffman codes. So as some background, we need to talk about ASCII characters. And so the ASCII table has 128 characters in it, mostly printable characters, but a handful that are non-printable characters. And so this requires 7 bits to encode these. Why 7? Because log base 2, because we're doing a binary system, of 128 is 7. And so, for example, the ASCII value 7 is a non-printable character, a beep. Try it out sometime on an old computer. There's also an 8th bit for parity, and so we get an even byte for each of the ASCII characters. And so what we want to do for Huffman codes to achieve file compression, though, is assign the most frequent characters to the shortest codes, because that's not how the ASCII table was constructed. Each one has the same length, and that has advantages to it. So if we can assign the most frequent characters to the shortest code, then this will reduce the number of bits required. We can generally save about 25% for large files and even 50 to 60% for some large files. Let's go through an example to see how this works. Let's assume that our entire alphabet is comprised of A, E, I, O, U, Y, and exclamation mark with the frequencies shown here, 20, 30, 24, 26, 8, 6, and 1. That gives us a total of 115 characters. Now this assumes that that's the entire alphabet, that's the only characters in the file, but it's a introductory example to show how it all works. With those frequencies and 8 characters, we only would need 3 bits to encode it. So we could arbitrarily assign A to be 000 and E to be 001 and just count up and assign each of the 8 codes to these 8 characters. Now if we just arbitrarily assigned it like that, we would get a total number of bits needed for the document for all the A's, the 20 A's, each having 3 bits would be 60 bits. And all the E's, the 30 of them, each requiring 3 bits would be 90, and so forth. This gives us a total of 345 bits with these frequencies and these codes. What we're going to do is we're going to store the characters in the leaves in a tree. And when we traverse the left child, we're going to append a 0 to the prefix, and traversing to the right child appends a 1 to the prefix. Let's see an example of this. Here we have those characters, A, E, I, O, U, Y, and exclamation mark as the leaves of a tree. And we, as mentioned, if we traverse left, it's going to be 0. If we traverse right, it's going to be 1. This leads to encoding 0, 0, 0 for A, 0, 0, 1 for E, and so forth. And so as we are decoding the binary, then we can determine deterministically which character it's supposed to be. We can also see here that when we get to 1, 1, we already know that it's going to be an exclamation mark, and we don't have to wait for the next bit. So we could save a little bit there and just encode it as 1, 1. That's a savings that we could implement. So if we were going to encode a string with these codes here, we could come up with an arbitrary, I came up with an arbitrary string. So if we had 0, 0, that'd be an A. If we had 1, 0, 1, that would be a Y. 1, 0, 0 would be U. Another 0, 0, 0 would be another A. Another 0, 0, 0, another A. and another U, and another A. So if we had that binary string, that would correspond with those characters. Let's talk about Huffman encoding. So Huffman, a couple of years ago, presented a greedy algorithm to determine the optimal solution for encoding the bits. So the algorithm is assign each character to a node, and thereby making each one to be a tree. And we're going to assign the frequency of that character as a weight. Then combine the two trees with the smallest weights and as children into a new tree, and assign the weight of that new tree to be the sum of the weights of its children. And step 3 is, as you probably guessed, repeat step 2 until all trees are combined. Let's see that algorithm played out. Let's use the same frequencies of characters and how they would work. So here I have those characters. I have sorted them now by the frequencies, and so we could show the weights here of those trees based on the frequency of each of those characters in the document. So we've done step 1. We've assigned each character to be its own tree with its weight. Step 2 was to combine the two trees with the lowest weight. That's going to be the tree with exclamation mark and Y. We combine those together, and we assign the sum of the weights to the new tree. And step 3 is repeat. Now we look again for the smallest two weights. That would be our combined tree rooted at T sub 1 and the tree U. So we'd combine those. They would have a combined weight of 15. We'd apply the algorithm again, looking for the trees with the two smallest weights. That'd be 15 and 20. Combine those into a tree with the weight of 35. Now notice the next two trees with the smallest weights are I and O. We're going to combine those into its own tree, and we'll continue on. Step 2 again, combine the two trees with the smallest weights. That's going to be 35 and 30 now. And we'll put the tree with the greater weight on the right. So now we have just two trees left, one with a weight of 65 and one with 50. So we combine those together with the tree with the larger weight on the right, producing a single tree. There we have it. We've produced our Huffman tree. Now we just need to apply 0 and 1 to the left and right children to know what the codes are for each of these characters. So now I is 0, 0, O is 0, 1, E is 1, 0, A is 1, 1, 1, and so forth. Let's enumerate these. So our most 0, 0 as I mentioned, and 0, 1, and then I is 1, 0. Notice that the most frequent characters here have 2-digit codes. And then as we go to lower frequency characters, they're going to have longer and longer and longer codes as we go through. Now we can calculate the total number of bits needed for that file. A is, well, let's start with the E, the most frequent one. We're only going to need 60 bits for it. Although it appears 30 times, it only requires 2 bits. The next most frequent character is O, again 2 bits, so 52 total bits, and so on. And this gives us a new total of 287, which is down from 345. Let's see an example again of that encoded using the new codes here. So using the same letters, we would have A would be 1, 1, 1, and then we would have Y, and then U, and then A again, and then A again, U, and A. Now, it just so happens that this one is actually longer, but why is that? Because it's using the characters that are not the most frequent ones. But if we stayed with E, I, and O, sorry, that would be it would be even shorter. That's my video. I hope you enjoyed it.